we already talked about loss functions. That are the functions that are using during the training to optimize the model. The problem with loss functions is when we are evaluating or judging how good the model, the already trained models are doing, is that those values from the loss functions, they can return any value between 0 and infinite. And depending on the data, on the prediction values, on the model you're using, it's really difficult to interpret that. And you may want to prioritize different types of mistakes or correct predictions when you are judging your model. One typical approach to evaluate and dissect the performance of your model that you see a lot often when you read machine learning papers is the confusion matrix. So the confusion matrix consists of a very good starting point. I usually personally start looking at the performance of the model after training it by looking at the confusion matrix and other additional accuracy scores later that I will describe. The confusion matrix consists of a table where you put the predicted class, like 0, 1 case control predicted value, and the true class in your classification problem, right? We're talking here about binary classification or categorical multi-class classification model. So you put predicted and true values on two different axes, and then you put whenever the model does a correct prediction, you count as in this diagonal axis, right? So true positives mean that the model predicted a positive value, predicted 1 when the true value is 1. True negative means the model predicted 0 or control when the true value was actually negative or control. So those are the correct predictions. And then on the other axis, on the other diagonal here, we have the mistakes. For example, if the true class was positive, but then the model predicted negative, so you have a false negative. If the true class was negative, but then your model predicted positive, then you have a false positive. So the first letter here, true or false, means correct or mistake. And then the second letter here means positive or negative, case or control. What is the true label, right? So it's just to make it easier to memorize. After you count those values, how many times the model got it right or wrong for each one of those combinations, then we can start to derive additional calculations of accuracy that will give us a number that goes between 0 and 1, where in all those calculations, it will give you a number that is between 0 and 1, where 0, the model is completely random. It's basically throwing a coin, heads or tails. The model is not accurate at all. And then 1, the model is perfect. Every prediction is right. But these different accuracy metrics will prioritize different things. It will be slightly different. So, for example, the traditional accuracy is what fraction of all the predictions are correct, right? So if the model got half of the predictions correct, then the accuracy score will be 0.5. This accuracy metric is only good when you have perfect balance in your data set, like 50% cases and 50% controls. Otherwise, you're gonna fall into the trap of the accuracy paradox, which is, for example, if 99% of your data are controls and your model predicts 100% controls, it's just a model that keeps repeating zeros forever, then your model will be 99% accurate. So accuracy is a terrible measurement. This first one is a terrible measurement of actual model performance when you have strong data imbalance. You have many more zeros than ones, many more controls than cases, right? Then we have precision and recall that are slightly different. They calculate different aspects of the correct versus wrong predictions. So the precision, for example, tells you, it asks, of the predicted positives, how many are truly positive? And then you have the recall or sensitivity that is from the true positives. How many of those did the model find overall, including the positives and negatives? So that can help you to spot why the model is failing, in what aspect the model is failing, because you're disentangled different aspects of the performance of the model. And then we have the F1 score that is calculated using those metrics, which is the harmonic mean of the precision and recall. That one helps you to have a more balance, penalize more for class imbalance, get a more realistic estimate compared to the accuracy value here. It will penalize when you have class imbalance much better than this traditional accuracy value. And we also have the receive operating characteristic curve area under the curve, which is another metric that tells you how well the model ranks positives above negatives across different thresholds. So whenever we train a classifier model, remember that I showed before that the classifier model outputs a probability. It outputs a value that is converted into a probability that goes between 0 and 1. By default, to make a call, a decision on whether the predicted value is 0 or 1, we use a threshold for that for that probability value of 0.5. But you can actually change the threshold if you want. Sometimes you find out that a slightly lower threshold than 0.5 or a slightly higher threshold, probability threshold than 0.5, it will give you a better performance, a better precision or a better recall or a better accuracy score, depending on how you decide which threshold will be used to call controls versus cases. So here in yellow, let's say you have negatives, and then in purple you have positives, hypothetically. So you can change those thresholds and create a curve like that for each threshold, right? Then when you create the curve like that, you can calculate the area under that curve of false positive rate versus true positive rate for each of those thresholds. And this area under the curve tells you how well that model is separating, ranking those two classes for each one of those thresholds and across all thresholds overall, right? Because you calculate every single threshold, calculate those true positive rates, false negative rates, precision, recall. And then after you have all thresholds calculated, then you calculate the area under that curve. That gives you a unified accuracy metric for your model, regardless of what threshold or across all thresholds, let's say, that you choose. Because if you calculate only accuracy or only precision or only recall, those values will change depending on the threshold you choose. AUC will not change depending on the threshold you choose. So AUC is a more unified approach when you are using those classifier models. When to use each one of those accuracy metrics? I end up, personally, I calculate all of them to have an overall view of how the model is doing, depending on different application contexts or different performance aspects of the model. So I start with the confusion matrix just to see all the types of correct and incorrect predictions. And then I use accuracy when I have like a balanced data set. Otherwise, I'll still calculate it, but I'll not trust on it at all. Then I'll use precision when the false positives are more expensive. You can use recall when missing positives has a high cost as well. For example, in clinical studies, you want to save as many patients as possible. Like this is screening, and you can use F1 score when you want one score that combines the precision and recall under class imbalance. AUC is a good complement as well. You just gotta be mindful that AUC doesn't penalize as much for data imbalance as F1. So you usually see an AUC score that is higher than F1 if you have rare true classes, so if you have a imbalance data set. So moving away from classification tasks, going into regression tasks, into regressor models, we have different ways a different way of evaluating the models. We cannot use those probability-based accuracy metrics or class-based, because we don't have classes here. We have continuous values in this type of models. So for continuous outcomes, we have three very common types of accuracy metrics. We have the mean absolute error, the mean squared error, and the R-squared. The mean absolute error and the mean squared error, they measure the size of the prediction error, and the R-squared measures how much of the outcome variation the model can explain, so the interdependency between the predicted and the true values. So the mean absolute error is just the average, is very similar to the mean square error that I mentioned before, is the average absolute difference between the true and the predicted values. So it's the same formula as down here, but without the square component. This is easier to interpret than MSE because the units, the range of the MAE value that you get as a result is the same range as the outcome. So you get a more intuitive notion of how wrong the model is relative to this range or size of discontinuous outcome. And then the mean square error is the average of these squared prediction errors. It will amplify those larger mistakes. So it's not a linear calculation of the amount of error anymore. But then it's more difficult to interpret. It's less intuitive. And then we have the R-square, which is a measure of how much the variance in the outcome is explained by the model. This is a lot more intuitive because MAE and MSE, they can be any number from 0 to infinite. So sometimes if you don't know the range of your outcome or how big is a bad MAE or MSE, R-square is perfect because we get back to that 0 to 1 range. You can also have negative values sometimes if the model is predicting exactly the opposite of what it should be predicting, right? Because the predicted and the true values in a continuous outcome, they can be flipped sometimes if your model was designed wrong or there's a data issue. So -1 also means the model is completely flipped. 0, the model is just random. And then 1, the model is perfect. So you get a much better feeling of how your model is doing if you calculate R-squared. Just to show here how the R-squared is calculated, you can calculate either this way or this way. So first you have to calculate the sum of the square differences between the predicted data points and the mean of the response variable. So you have the mean here and the predicted values. And then you calculate the sum of the square differences between the individual data points, the ground truth values, and the mean of the response variable. So you can divide it like that, or you do 1 minus the square of the differences between the predicted values and you observe the ground truth values, and then you divide that SSE by the SST, 1 minus that, and you have your R squared. There is also an adjusted version of this R squared that takes into account the sample size, but for sake of time, I'll not cover that in much detail here. So just to summarize, like MAE is the typical absolute error size. Mean square error, MSE, is it punishes more larger errors, and then R squared is how much the variation of the true values the model can explain.